Have you ever really stopped to think about how you're watching this right now? I mean, you click a link and boom, information just zips from a server that could be thousands of miles away right to your screen. It feels like magic, right? But it's not. It's this incredible technology that quietly powers our entire modern world, the Wide Area Network, or WAN. So let's pull back the curtain and see how it all really works.
So this is the big question we're going to tackle. It's one thing to connect to a printer in your own room. That's easy enough. But it's a completely different ballgame to pull up a website from a server in, say, another country. How do we possibly bridge that huge geographical gap, not just reliably, but instantly? Well, that's what we're here to figure out.
The whole answer really starts with getting two key ideas straight. You're probably already familiar with a LAN, or a local area network. That's your home Wi-Fi, your office network. It's a small private network that you control. But to get outside your own building, you need something way bigger. So think of it like this. Your LAN is your personal driveway. To get anywhere else in the world, you have to connect to the WAN, the massive global system of highways.
Okay, so if a WAN is this giant system of highways, how are those highways actually laid out? Well, just like a city planner has blueprints, network engineers use these core designs called topologies. These are the fundamental patterns for how everything gets connected in the first place.
The simplest blueprint of all is point-to-point. Just imagine a dedicated private road connecting your office in New York directly to your office in London. Super straightforward, super reliable. But you can probably see the problem, right? If you open a third office in Tokyo, you need to build more private roads. This gets really expensive, and it gets expensive fast. So a much more common design is the hub and spoke model. The best way to think about this is like an airline. All the smaller airports, those are the spokes, they all connect to a major central hub, like Chicago O'Hare. If a branch office in one city wants to talk to another branch, that data has to fly through the main headquarters hub first. It's pretty efficient, but it also creates a massive single point of failure. If that hub goes down, the entire network is grounded. Now, for the gold standard for maximum reliability, you have what's called a full mesh. In this setup, every single site has a direct connection to every other site. The result? It's incredibly resilient. If one connection fails, no big deal. There are tons of other paths the data can take. But as you can probably imagine, this is by far the most complex and the most expensive to build and maintain. But here's the thing about the real world. It's almost never just one or the other. Any big global company is going to use a hybrid model. They might use a hub and spoke design for their smaller regional offices, but then connect their huge data centers with a super reliable full mesh. It's always about finding that practical sweet spot between cost, efficiency, and reliability. To see how all these choices actually play out over time, let's follow the journey of a fictional company. We'll call them Span Engineering. We're going to watch them grow from a tiny startup into a global powerhouse over 20 years and see exactly how their network had to evolve right along with them. So, in the beginning, year one, SPAN is just a small office with a single LAN, your basic internet connection. But by year 5, they're growing. They're taking over multiple floors, and they need a real campus network with their own IT staff to manage the whole thing. Fast forward to year 10, they're going national, opening up branch offices and connecting them with these expensive, private, dedicated lines. And after 20 years, they're a global enterprise, connecting thousands of employees all over the world, not with those pricey private lines, but with flexible and secure virtual private networks, or VPNs. Every single stage of their growth forced a complete rethink of their network. Span's journey brings us right up to the present day. So what are the tools and technologies that make all this modern global connectivity possible for companies like them? And, for all of us. Let's open up the toolkit. The first big choice you have to make is between a private or a public WAN. A private WAN is kind of like leasing your very own personal highway. It's dedicated just to you, so you get guaranteed speed, guaranteed security. A public WAN, on the other hand, uses the internet, the shared public highway system. It's way more flexible and affordable, but your performance can change, just like hitting rush hour traffic. So how do you get the security of that private road while using the public highway? Well, that's where the VPN comes in. A VPN creates a secure, encrypted tunnel for your data right through the public internet. It's basically like putting your information inside an armored car that travels on the public highway system. It's a really clever solution that gives companies the security they need with the scale of the internet, all for a fraction of what those private lines used to cost. Of course, to even use the internet, you need an on-ramp. This table breaks down the most common options. You've got DSL, which uses old phone lines, and its speed really depends on how far you are from the provider. Cable uses the TV network, but you share the bandwidth with all your neighbors. Then there's fiber, which offers incredible speed, but you have to install new lines. And of course, you have wireless options like cellular and satellite, which are amazing for remote areas, but they have their own trade-offs with coverage and cost. The key takeaway here is there's no single best option. It's always a balancing act. Okay, now for a quick peek behind the curtain at how the service providers actually manage all of this traffic. They use this really powerful technology called MPLS. Think of it as the internet's express mail service. When your data packet enters their network, MPLS slaps a special label on it. That label tells every single router exactly where that packet needs to go, which lets it get forwarded at incredible speeds. And it doesn't matter if it came from a DSL line, a fiber line, or anything else. It's the high-speed sorting facility at the heart of the internet that makes everything feel so fast. For any business, uptime is everything. So how do they make sure they stay connected? Well, they build in redundancy. The most basic setup is single-homed, one link to one provider. If that goes down, you're offline. A better way is dual-homed, 2 links to the same provider. Better still is multi-homed. Now you're connecting to 2 different providers. And for the absolute maximum resilience, you have dual multi-homed, multiple links to multiple providers. Sure, it's the most expensive, but it's as close to bulletproof as you can possibly get. So, we've covered the blueprints, the technologies, the strategies. When you put all of that together, what do you get? You get this invisible infrastructure that supports almost every single aspect of our modern lives. What is so special about the number 53? This is a little piece of internet history. It is the fixed length in bytes of something called an ATM cell. Asynchronous transfer mode was this cool technology that chopped up all data, voice, video, you name it, into these identical tiny 53-byte packets. Now, why does that matter? Because by forcing all data into these tiny, identical packets, ATM made it possible to build hardware that could switch them at unbelievable speeds. This idea of standardization was a fundamental breakthrough that really paved the way for the high-speed internet we all rely on today. And this is why all of that technical stuff matters so much. When you stream a movie, or you jump on a video call for work, or you buy something from a store on another continent, you're using this system. All of it is powered by that incredibly complex global web of wide area networks. It really is the circulatory system of our digital world. So the principles we've talked about built the network that we have today. But we'll leave you with this question. As we start connecting billions more devices, everything from smart cars to a global Internet of Things, the demands on this infrastructure are going to be absolutely immense. What new topologies, what new technologies, and what new ideas are we going to need to build the network of tomorrow?